In the next couple of videos, I will explain how you can construct lattices from the elliptic function fields by mainly following this research paper. You can find it on the Scholar, but at the end of these videos, you should be able to follow the material which is presented in this published paper. Before that, let me remind you how we define elliptic function field last week. Even though we are in the case of function fields over finite fields, we define an elliptic function field as genus 1 function field involving a rational place O. And we denote this rational place by O because we want to also see that this fixed rational place behaves like identity in the group structure on the set of rational places. And in that we have seen that if we have such a definition by using the consequence of the Riemann-Roch theorem, we can describe our elliptic function fields in terms of the simple extension involving k, x, and y, where the transcendentals x and y, they are transcendents over k, are in the algebraic relation as y squared equal to f of x, where f of x is degree 3 square-free polynomial. Indeed, this setting was based on analyzing the Riemann-Roch space of the divisors, the multiples of O, and we choose the function x inside of the Riemann-Roch space of 2O, but not in O. Because of the dimension argument, we have proper inclusion. And recall that this tells us the pole divisor of x in F is exactly 2O. And we chose the function y inside of the Riemann-Roch space of the divisor 3O, but not in 2O. So that means the choice of the function tells us the pole divisor of I is exactly 3O. So that means O is the unique common pole of x and y in the elliptic function field. And if this is the case, like if we have the definition of elliptic function field in terms of genus and in terms of the existence of a rational place, we can derive this equation. And in Schtitt you can also find the other way around. Indeed, this is a characterization, but it requires some tools, advantages from the expansions of algebraic function fields. Another important property, we studied the set of rational places is a one-to-one correspondence with a class 0 group. Indeed, this bijection given by mapping the rational place to the class of P minus O. And thanks to this bijection, we were able to remove the group structure of the class 0 group to the set of rational places. And we defined the addition of the set of rational places by using the equivalence of divisors. This is divisor equivalence, and O is the rational place we fixed in the beginning. And today, first we elaborated if this is divisor equivalence, we know the existence of a non-zero function by the definition of the equivalence divisors, which gives us this equality. And in the last lecture, I tried to elaborate how does that look like, how does that can be described geometrically, but I will explain it again. And another important information that will be important today will be if we have two distinct rational places, P minus 0 is 0 divisor, but it cannot be principal. So the Riemann-Roch space is going to be trivial. So if it is not trivial, it has dimension 1, then they should be equal to each other. By the way, maybe I should mention that, like in terms of, because k equal to k is not correct. Like it's going to be 0 divisor. Actually, it's correct. Sorry. So it has dimension 1. And if you have seen an elliptic curve course, in general, elliptic curve is defined as a solution of this equation over a field K. By the solutions, what we mean, 2 tuples from K, the entries from K, which satisfies this equality. And for the simplicity, in general, they consider a picture over R. Actually, it has several pictures, but interpretation of this picture is easier than the other pictures. And regarding this picture, we can also define the point addition on this structure geometrically. And this is described as like, if we consider a line passing through P and Q, based out from the algebraic geometry, this is called Bezout theorem. Don't confuse with the Bezout's identity. We can guarantee the existence of the third point as the intersection of our elliptic curves and the straight line. And the addition of P and Q is defined by taking the reflection of this third point with respect to the x-axis. And here, I will denote this line. Indeed, it is in the line equation, ax plus by plus c, a, b, c are constants from k, but this x and y are also transcendental, which appears in the elliptic curve equation. And I denote this line. This is a line passing through the points P and Q. And indeed, this is a function, right? Because x and y are function. In our function field, the k linear combination should be also function. So we can talk about its principal divisor. So with respect to this geometric interpretation, we can see that, like, if P and Q satisfies this line equation, also R prime satisfies this equation, we can see that P, Q, and R prime are the zeros of this transcendental. So the zero divisor of this line in the P plus Q plus R prime, and there is no any other point in this intersection. But we know that every transcendental should have at least one pole, and the pole order and the zero degree of the zero divisor and the pole divisor should be the same. And my claim is that its pole divisor indeed minus 3O by using this fact. Because we know that the pole divisor of x is 2O, which means VO of x, we can work with discrete valuation maps, is minus 2, and for any other places different from the identity, VP of x should be bigger than or equal to 0. And similarly, we have the same property for the function y. And thanks to this fact, we can see that O is the only pole of this transcendental, this line, and its multiplicity is 3 by working with strict triangle inequality. In the meanwhile, we also have another line. And let me denote this line by x minus x of r. By the x of r, what I mean, the x coordinate of the point R. So, I mean, if R is given by R1, R2, it's going to be exactly R1. And if you look at this transcendental, x minus x of R, it should also have at least one zero and one pole. And we know that R and R prime satisfies the equation because they have the same x coordinate. This is going to be zero divisor of x minus xr in the function field. And similarly, we can verify that O is the only pole of this transcendental because O is the only pole of x. So this is a constant. And its multiplicity is -2, again by working strict triangle inequality. Now let me consider the ratio of these two transcendentals. And let me look at its principal divisor. And by using the definition of the principal divisor, which involves the discrete valuation maps, we can see that this principal divisor is equal to the principal divisor of M of P and Q minus x minus x of R. And we computed this principal divisor as P plus Q plus R prime minus 3O. And this principal divisor is computed as R plus R prime minus 2O. By using the properties of the divisors, we can see that this is indeed equal to P plus Q minus R minus O. Indeed, this is the function Z, which gives us the equivalence of P plus Q R plus O, and this equivalence, recall, that gives us the addition on the set of rational points. But in this case, like we explained this situation for distinct P and Q, and this P and Q are not the identity, right? But we might be in the scenario of that P and Q can be located such that P plus Q is equal to O, like the point at infinity. So its reflection with respect to the x-axis again is going to be O. In this case, we want to look at how this equivalence look like, or what kind of function which gives us this equivalence. Again, we use the same approach. Let me denote the line which passing through this P and Q by M of P and Q. And in this case, the principal divisor M of Q is going to be P plus Q like the but I mean this is going to be the line like in the form of x minus the x coordinate of something, right? So we only have two zeros, which is located in the intersection with this line and the elliptic curve. So P and Q are the only zeros. And its pole indeed 2O again, thanks to this observation. And in this case, one over P minus Q gives us this equivalence. Or the other way around, please check it. So this is the second scenario. And the last scenario we should consider is that In the addition P plus Q, one of them can be identity. So without loss of generality, let me suppose that the second point is the identity. So we want to look at, we pick a point P, and we want to see that like it should be equal to P because O behaves like the identity on the set of rational places. So P plus O is equal to P plus O. This is something trivial, right? So we need to get any constant. And for the geometrically, if you add like P and O, again, like you consider the straight line with O like passing through P and O, you take the reflection. So it is like you have the intersection here. Let's say P prime. And by the additive inverse, I will also use the prime notation. And when you look at its reflection with respect to the x-axis, you again the point P. In this case, we have like sharp equality for this divisors. For this Z, the possible candidate can be a non-zero constant one. So regarding these fractions and these functions that which gives us the equivalence, let me fix the notation if P and Q, this is the function which relates to the points or the set of rational places P and Q. I will use the rational points of elliptic curves and the rational places interchangeably. And we will set this function f by looking at the fractions, like, or the inverse of this type of fraction. So, I mean, you are just changing the sign of the divisors when you look at 1 over z. But I will follow the notation which is given in this paper. And in the first scenario, I will consider in this scenario where P, Q, and R different from then the identity. I will consider the function f as the fraction of x minus x of r over npq. And if P and Q are different from identity, but their sum is identity, so P and Q are additive inverse to each other, I will consider the function m of pq. And for the last case, if P or Q is identity, I will consider the constant. This is the one fact, and we will work with this type of functions. This will be important to derive, to study lattice structure of the elliptic curves. And another important fact, like this is a general result, we can make an observation for any function field. If we have a divisor D, and if we have a function f or z, then f times L of D, so this is the set f times x where x in the Riemann space of D, indeed equal to the Riemann space of D minus the principal divisor of f. This is going to be in your exercise, and we will talk about in the Zoom session. And now we can state our first proposition. I am following the enumeration in this paper. If we have two rational places in the elliptic function field f, then for a rational place R, P plus Q equal to R, if and only if the Riemann space P plus Q minus R minus O is different from than 0. And if this is the case, this is going to be like degree 0 divisor. And this is going to be principal thanks to this like addition structure. But this one-dimensional vector space, so if this is principal, it should have dimension 1. Indeed, this is not going to be constant always, but this Riemann-Roch space is spanned by the function f, p, and q. So the function we considered here, and in the next video, I will talk about its proof. But I mean, here note that it's not supposed to be always k. This is, even though this is isomorphic k, we might not get the equality because this function might have poles and zeros, but we know that any constant cannot have any zero or pole. So let me continue its proof in the next video.